Thank you for the introduction. Can you hear me and see my screen? All right, let me just start. So my name is Bai. I'm a postdoc researcher at National Renewable Energy Lab. Today I'll be presenting our paper titled Certification and Prediction of Post-Disturbance States in Dynamic Security Assessment. This is a paper with a collaboration with Rui and Feng, both from Argonne National Lab. So a few words on the motivation of the work. So this work is actually motivated by some implementation issues in dynamic security assessment. So in dynamic security assessment, one of the issues or one of the tasks we face is actually to compute the post-disturbance state in order to initiate the time domain simulation. And the state is determined by a set of algebraic power flow equations incorporating generator models and so on. One of the issues we face is that sometimes when we have a significant disturbance, the post-disturbance system state will deviate actually a lot from the previous, from the pre-disturbance system state. And this poses some computational issues. So the problems are as follows. First, the performance of some numerical solvers for the power flow equations depends heavily on good initial values. So without the knowledge of an approximate value of the post-disturbance system state, sometimes the numerical solvers will fail to converge. A follow-up problem to this is that when the numerical solver fails, when you cannot find the post-disturbance state, we actually have no idea of knowing whether the post-disturbance state actually exists, because it's possible that the system just collapses and there's no post-disturbance state, or it's also possible that the numerical solver just fails numerically. You cannot find the solution. So a natural question we ask when facing this dilemma is that, can we certify the existence of post-disturbance system state? And can we approximate the value so that we can, have a better warm start of our numerical solver without explicitly solving the algebraic power flow equations? And it turns out that this is the subject of study of the so-called power flow solvability problem, which has seen some research in recent years. So the specific problem description of the power flow solvability problem is as follows. So in this problem, we try to give necessary and/or sufficient conditions on system parameters, for instance, the load injection, the power injections, the generator voltage magnitudes, and network topologies, and so on, such that the power flow equations will have a unique high voltage solution. So the features of the solvability conditions are as follows. First, it gives us a certificate of solution existence and uniqueness without explicitly solving the power flow equations. And it also gives us a characterization of the voltage set where the solution will lie so that we can warm start on the solver. And then it also guarantees under some additional conditions, it guarantees the convergence of iterative power flow solvers to find the unique solution. It should be noted that most of the existing conditions work on a special type of system setup, which is a system composed of PQ buses, constant power loads, and slack buses. So in this work, we propose to certify the existence and predict the approximate post-disturbance state in DSA by extending the solvability conditions to incorporate the salient pole generator model. So the system model we consider is as follows. We know at the instant of system disturbance, the state variables in generator model, they stay the same. For instance, the rotor angle or the equivalent internal potentials and so on. So we can model the synchronous generator at this point by a constant voltage source. And it turns out we can also model some dynamic loads such as induction motors in this way. In addition to this, we have constant power loads and linear series or shunt components modeling the transmission lines. So since the last two components are familiar, I will just introduce the model of the synchronous generator for our study. So as we can see, this synchronous generator modeled as a constant voltage source can be cast in the following way, which relates the output current of the generator voltage of the generator to its terminal voltage, and also the internal potential, epsilon D and Q. It's worth noting that in the matrix, in the matrix preceding the epsilon D and Q, if chi D and Q are the same, then actually we have a non-salient pole generator model, and for that model, that model is actually a linear in phasor domain, which means it's equivalent as a constant voltage source behind the impedance, so that it can be incorporated in existing solubility conditions, but not for this one because we have different D and Q axis reactance. So if we stick with this model, we can formulate the overall system model by using the rectangular coordinates as follows. Where this augmented admittance matrix relates the current and voltage of all the system nodes augmented by the internal, augmented by entries representing the internal, the generator internal potential. And notice here we also have the nonlinear power flow equations describing the power balance at the load buses. So it turns out that for this model, it can be recast in the following fixed point form. Whereas we can see the, for instance, the first equation here actually relates the real part of the voltage I as a function of all system buses, all system bus voltages. So if we take a closer look at the fixed point form of the power flow equations, we see that it is a sum of two terms, where the first term is a Mobius transformation of the voltages, and the second term is just a translation. It's just a function of system parameters, for instance, the line impedance topology and the nodal power injections. So if we take a more closer look at this fixed point form and see what this mapping actually does, we can see that for this Mobius transformation, which is given by z minus 1 over z here, it actually maps the half plane h1 half, which is the half plane shown here with the real part of z greater than 1/2. It maps this half plane to the unit disk. So if we assume that for our bus voltages, they all have real part greater than 1/2, which is very common in a power system, then actually what this mapping does is that it maps this half plane to the unit disk. And then it scales the unit disk and then shifts it. So there's a scaling and translation given by this alpha and beta parameters. So what this mapping does is that it maps this half plane to some disks. And then we know that as long as each of the resulting disk, the image of this mapping actually lies in the half plane h1 half, then this fixed point mapping is actually a self-map. And this, the Cartesian product of all the disks D, which we denote by V here, is actually a forward invariant set. And what that means is that by Brouwer fixed point theorem, we can actually guarantee that there exists a fixed point, where in other words, a power flow solution to the power flow equations within this disk. So by this way, we derive the conditions, we derive the sufficient condition for the existence of fixed point, which essentially says that the real part of the center of the disk minus its radius has to be greater than 1/2. We can further derive sufficient conditions on solution uniqueness by characterizing the condition under which the fixed point power flow is a contraction in the voltage set. For the interest of time, I'm not going to the detail of this. For details, please refer to our paper. But it's worth noting here that the uniqueness condition is more conservative than the existing condition, which makes intuitive sense because it's a stronger condition. And what's interesting to note is that this uniqueness condition is a generalization of existing solubility conditions we found in the literature, even though the fixed point form that we cast is different. And another favorable feature of this uniqueness characterization is that it guarantees linear convergence of the fixed point iteration to find the unique fixed point. As we can see, the simulation results here shows that for some standard IEEE test systems, it actually converges to the unique fixed points fairly quickly. So next, let's look at some simulation results. So for the first simulation, we test our condition on IEEE 39 bus system. We assume there is a light ground fault at bus 6. And we simply check the condition satisfaction for different fault impedance. So as we can see from the table, except for the last row where the fault impedance is at the critical value, rendering the system to voltage collapse. For all other conditions, we can actually guarantee the existence of a post-disturbance state. And except for the last two fault impedance, we can also guarantee that the solution is unique within our characterized voltage set. And the voltage set looks like this. We can have an upper and lower bound on each of the voltages where the post-disturbance state will lie. And we also have a fairly good estimation of the state. So we also test this on a larger system, the IEEE 118 bus system. And the condition is fairly consistent with the previous experiment. It shows that except for the critical fault impedance, the existence of the post-disturbance state can be certified. And for most of the cases, the uniqueness can also be certified. We also tried this on a numerical solver based on a modified Euler and Newton-Raphson. And we see that during fault clearance, with fault impedance equal to 0.1 per unit, the solver actually diverges. So it's not able to find the post-fault system state, whereas our algorithm can successfully certify the existence of the solution and also characterize the approximate solution location. So in conclusions, in this work, we have extended the solubility condition to incorporate a Cillian pole generator model. And we have also applied the condition to certify post-disturbance system state existence and also give approximation on its values in the context of dynamic security assessment. We have also presented that iterative algorithm can be used to guarantee the finding of the unique post-disturbance state with this model. And some future works, including extending our work to more generic system models, which can include, can incorporate a three-phase system and additional devices. So there are also other applications of this solubility analysis for example, robust operation and control problems. For instance, robust OPF can use this condition, and also it can be used to do ultra-fast contingency screenings. So that's all for my talk. Thank you very much for your attention, and I'm open to questions. Are there any questions?
Sorry. I have the microphone in mute mode. Sorry. There is one question. No, there is sorry. There is one question by Dan. I will read it again. One question for you. How do you assure that your condition is capturing the high voltage power flow solution as opposed to a low voltage solution among the multiple power flow solutions that exist?
Okay, thank you, Dan. That's a very good question. Actually, in this work, there's no way of knowing this is whether this. So in our presentation, we didn't specify whether this is a high voltage solution, but as you can see from the slides here, it actually maps the half plane to the disk. So an easy corollary of this is that if we can certify solution existence, we can also certify there is a unique solution with voltage real part greater than 1/2. So if this is where the high solution lies, high voltage solution lies, then yes, with the uniqueness condition, we can actually certify that this is also a unique condition in this half plane. But without the uniqueness condition, of course, we cannot know whether there are other high voltage solutions.
Okay, thanks. The next question is by Nawar Nasir. Thanks, Bai, for the great presentation. From your simulation results, it seems that the approximated voltage underbounds the actual one. Is that something that always happens? Thanks.
Thank you, Nawaf. That's also a very good question and good observation. Yes, the approximate value actually in this case are consistently higher than the voltage than the actual voltage. I think that's mainly because of the fact that the condition doesn't consider the flow of the power, so it doesn't know if for load bus the power is injecting into the network or is being extracted from the network. So I think with that additional information, we can derive better approximate solution and maybe better approximate this.
Okay, thank you. There's 1 minute for one more question. I will make a question in this case. Your paper establishes a one-to-one correspondence between the set of fixed points in equation 12 and the set of power flow solution in 5 and 6. But what about the reactive power limits of generator? Because this could affect the solvability of the algebraic equation. These are additional nonlinearities. Are you considering those?
In this work, no. So in our case, we consider the case where the generator haven't hit the reactive power limit. But when it does hit, then when the generator actually becomes a transition from a PV bus to a PQ bus, then it actually can be incorporated into our model by considering the generator as a load bus, because the model, the method does have the flexibility to incorporate a PQ bus, whether it's a load bus or a generator bus. So yes, that condition can also be incorporated.
Okay,